Okay guys, welcome back. We are going to continue our discussion on transport through the cell membrane. We are right now looking at passive processes. Now we want to remember basics about passive processes, right? Passive processes are moving items from high to low concentration. They are not require energy versus active processes, which are the opposite. And the last thing that we went over was the fact that for certain things to move from high to low, there must be some assistance in the membrane through a channel or some kind of protein like that to allow something to move from high to low. And this is because a lot of items that are charged or too big cannot wiggle down through between phospholipids that are in the cell membrane. And in the barrier there, in that phospholipid bilayer, it's an oily kind of substance, right? It's not going to allow anything charged or too big to get through. And one of the items that we discuss being controlled in this way would be water, and the movement of that water would have to be assisted by some kind of a water pore made out of a protein. Now, this would be osmosis, right? So we have basically a special name for facilitated transport, a passive process, where it's facilitated by a protein, but in this case, it's water, which is a special molecule, so we give it a special name. Now, a lot of times in your textbooks, your text has a little bit different kind of figure, but they throw these pictures at you, and you might think, well, that doesn't look like a cell, and certainly these are not cells, but they have these two pipes, right? They have these two U-shaped pipes, and they are showing water inside these pipes, right? And they're saying, okay, imagine like there's a permeable membrane in between the solutions, the fluid, on either side of this pipe. And they're saying, imagine if this membrane is permeable to solutes. So this is to say, in our little example here, let's say we have these red dots, and these red dots are a solute. So a solute is something dissolved in a solvent, right? A solute is something like maybe a salt that might be dissolved in water. So here, let's say that's a salt. Let's say that's sodium. And there's so many red dots here, so many sodium particles there. And then on the other side, on the right side, we have many more sodium particles. And they're saying that that solute is able to go through these pores, okay? Now, if that's the case, and the sodium is able to move freely, we would expect it to go from high to low. That's the way chemistry works, right? So we'd expect this to happen here. This red dot would move naturally across. This other one would move naturally across. And this would just happen until the two sides would be fairly equal in concentration. And you might expect this to be the result over on the right side, right? We would have a movement of those solutes. If there are channels open for sodium, this is how it would work, right? And it would go until the two sides were equal, okay? This is not osmosis because it would be the movement of the solutes, not the water, right? So if these were permeable to the solutes, the salt would move, and this would make the two concentrations equal. Okay, so now let's change this a little bit. Let's say that we have a pipe like you see here, all right? And we'll bring out the pictures first, and then we'll talk about some of these other things. So let's say now we've got a similar situation here on the left. We've got this permeable membrane, and we have these solutes in red. Let's say it's sodium again. But now imagine if the membrane is actually impermeable to the solutes. Let's say that only water is able to pass now, okay? Now, if only water is able to pass between these two sides, until the concentrations are equal on both sides, well, we would have to assume, I'm going to change this to blue here, we would have to assume that the blueness on the left side, all of these that are representing, all the blue here that's representing water molecules, would have to move the other direction, right? There's less blue on this side where there's lots of red dots, and there's more blue on the side where there's less red dots. And if only the water is able to move, so we'd have to assume that maybe there's some proteins that are pores for water. If those are there, then the water is going to move to the other side, okay? And you would see what the result would be if this occurred, right? This other side, there's only so much room, and the water would just keep moving over there until the two concentrations of the sodium in that water was the same, okay? Now you notice that the solute would move a different direction than the water would move given the chance, right? But still we're moving from a position of high to low. In the previous slide, I'm going to go backwards here, okay? We had the red dots moving from one side to the other, right? From the right side to the left side, because it's just trying to make the two sides equal. Only the solutes were able to move, okay? For this particular one, they're saying that only the water is only able to move. Very different situation. The water is going to move from the other side to where there's more red dots, okay? Now, let's imagine this is actually a cell, just for argument's sake, to make more sense of this, okay? So let's say we have a cell. So here I'm just going to use this yellow line, and this is representing a certain amount of space over on the right. Let's say that's now a cell, right? And let's say now water pores are open. So I'm going to use blue and say, okay, here are our water pores. All right. And we ask, where will water move? Well, we just determined that water is going to move this direction, right? Water is going to move over to this side. And after a while, after water is doing that, we're going to end up with more fluid in general on that right side. So imagine how that's going to feel for this cell as it engorges with water, right? This particular cell, we might imagine that this cell is really going to get big, right? It's going to really blow up with fluids, okay? And that pressure will be felt within that cell, okay? This osmosis is going to cause the pressures to rise within the cell, and we have a name for that, okay? As osmosis occurs over into that cell, we would have to imagine that there would be more and more pressure, okay, against the inside of the cell's membrane. It's just a physical push that's going to be felt, a physical exertion as a result of all of the fluids that would build up in that cell, right? This is what we call hydrostatic pressure. It's a physical push exerted by a solution against a membrane, right? So if we have a cell and we put it into a solution that's rather dilute, right? Lots of water compared to what's in the cell, we would expect this cell to blow up and have a lot of what we would call hydrostatic pressure against the inside of that membrane. That's hydrostatic pressure, a physical push exerted by a solution against that membrane. Now, there's still going to be a movement of water into that cell as long as there is a more dilute situation outside of that cell, okay? The tendency for the water to move into that cell is called osmotic pressure, okay? So we have an osmotic pressure, which is a pull into the cell. Do you see how it's a pull into the cell? All of these red dots that are found inside the cell are kind of like a sponge. The fact that it's still concentrated inside of that cell or on the right side of that tube means that it's going to be soaking up that water, pulling that water in. This is called osmotic pressure. And it will continue to do that until the two sides are equal. Okay? So we have hydrostatic pressure, a physical push, and we have osmotic pressure, a pull, a tendency for water to move into this cell because it's more concentrated with sodium on that side. Okay? All right, so let's use a real-world example using red blood cells. Okay? A red blood cell should look something like you see over here. It's kind of a weird kind of circular pillow. I think of those pillows like for an airplane where they have a thick side and a thin part. Okay, so this is the way a particular red blood cell should look. Okay, it will have a certain amount of fluid inside of it. It won't be too much pressure inside, and it won't be too little pressure inside. Okay, what we hope is that not too much water goes into any cell in our body, or else we could be in trouble. That cell could burst, okay? So when we talk about osmosis, we pay attention to the tone, the pressure exerted against the membrane of our cells, okay? If there's more water that goes into a cell, you would expect for that tone, that pressure, to become more and more, right? The hydrostatic pressure would rise within a cell. And if we have a lot of water leave the cell, we would expect for the cell to shrink up, right? Not to look right after it lost a lot of water. So what we hope is that water is not going to move freely into the water too much, and it's not going to move freely out of the water too much. What we need to realize is that water pores, imagine water pores throughout this entire red blood cell. Water pores are always open in human cells. And these water pores will allow water to move freely. So what we hope is that there's not a big difference in the concentrations on either side of these membranes. If there is, the cell is going to shrink, or the cell is going to blow up like a balloon and maybe even burst if too much water enters. Okay? Now this is not an issue with a plant cell. The reason that it's not an issue with a plant cell is that plant cells have a cell wall. Plant cells don't just have this membrane maintaining the boundary of the cell, but they also have this thicker outside cell wall. So if water freely goes into a plant cell, well, it's not going to necessarily destroy that plant cell. Okay? So we talk about the tonicity of an animal cell, and we hope that there's a nice balance between the outside solution and the inside solution. There are three basic states we can think about when we compare the concentration of fluids outside a cell to that inside of a cell. If the concentrations inside of a cell and outside the cell are the same, we would say that it is an isotonic solution outside of that cell. The solutions have the same concentration, and when we look at cells inside of our body, that concentration happens to be about 0.9% saline. So a salt solution at 0.9% would be about equal to the concentration inside of our cells, inside of this red blood cell. Or if you had a 5% glucose solution, a sugar solution, 5% sugar is about equal to the concentration of all the stuff that happens to be dissolved inside of a cell or a red blood cell. So this would be an isotonic solution. And in fact, if we look at the plasma, the liquid components outside of our red blood cells in our blood, plasma is indeed isotonic. The concentration of all the things in the plasma is roughly equal to the concentration of all the things in our red blood cells. And hence, our red blood cells look like this. Now, what if a cell was in a hypertonic solution? Okay, so this is saying that there's more of something, right? Hyper. If you're hyper about something, you're more excited, right? Well, if you're hypertonic, if we talk about a solution that's hypertonic outside of this red blood cell, well, that would mean that it's saltier. There's more solutes in the solution outside of that cell. Now, let's think about that, right? If there happened to be, I'm going to just make up a scenario here. Let's say inside this cell, there's 1, 2, I'm going to just make a bunch of dots, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I were to compare the plasma of our blood to the concentration inside of this cell, well, we might find 12 outside. 1, 2, 3. They don't have to all be the same color. Various different solutes. They don't have to be the same solutes. So here we have 6, 7, 8, 9, 10, 11, 12. Isotonic, right? Same concentrations on either side. What if we were to add 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so now I've made it more salty outside of that cell. And like I mentioned, only water can move through these pores, remember, okay? So, which way is water going to go? We have inside the cell where it's more dilute, more water in other words, not as concentrated with solutes, but more water, and outside of the cell where it's more concentrated, less water in other words. It's going to be like a sponge, right, for water. So which way is water going to go? Well, water is going to move outside of that cell. If this happens for a while, guess what you're going to end up with? You're going to end up with this right here, what we see over in this second picture. The cell is going to lose water, okay? And as it loses water, like that, like I just drew over on this side here, we're going to end up with a shrunk cell, all right? It's going to shrink because the concentration of the fluids outside is too concentrated. This will happen if you put red blood cells in a concentrated sugar solution, more concentrated than 5%. This will happen if you put these cells in molasses, right? So if you had like a thick sugary solution at home, like a sugar solution or something, and then you put red blood cells in there, you would find they would shrink up like this. This is not natural, right? We wouldn't find this typically in a normal healthy individual. We'd want isotonic. Okay, last one. Let's say we took this cell, this normal red blood cell, and we have it on a slide, and then we add pure water. Okay, so we'll make some dots. 1, 2, 3, 4. We'll make it like last time. 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, we made it 14. Okay, so 14 solutes dissolved in that cell. And now let's say outside of the cell, we have pure water. So over here, off to the side, right, we have pure water. That means there's no solutes at all. It's not concentrated at all, right? So where is there more water? Where is it more dilute? Outside the cell. It's pure water. Now, if we have water pores that are going to allow that water to move freely, well, now we're going to find that that water is going to move into the cell. In fact, it will move into the cell forever, won't it? There's not going to be a point where the concentration of solutes inside the cell is going to be the same as outside. And so this would just happen until probably the cell would burst, right? There are no cell walls. Now, over here in this image over on the right here, they're showing you that very situation where the cell in water is going to actually blow up, right? It's in a hypotonic solution. Hypotonic because there's less solutes, hypo, right? Water, pure water, would be the most hypotonic thing you can have, right? And so the water is going to go in, and this might eventually burst. Now, in real world situation, where do we see this? If someone is dehydrated, right? Terribly dehydrated. They've sweat a lot, right? They haven't gotten enough water into their system for the entire day, let's say. Or maybe they have some kind of condition where water is being lost from the body, like a diarrheal disease, or they're vomiting from an infection. Well, you'd lose a lot of liquid that way, right? To help someone who's dehydrated, you might give them a hypotonic solution. You might give them more of a watery kind of solution in an IV, maybe. Okay, hook them up to a tube that will allow a more watery environment into their body because they are dehydrated, right? So it'd be a real world situation where you might need to use that knowledge to actually help someone. Okay? All right. So here we have a little video. I found this on YouTube, and I'm going to link to it, okay? But you can actually test these ideas with eggs, okay? Eggs are just huge cells, okay? So eggs, of course, have a wall, okay? They're not a cell wall that would be made out of cellulose, but they're a wall of, I think, calcium and carbonate or something like that. So they're made of calcium. And you can dissolve that calcium away if you put eggs into vinegar. So if you put eggs into vinegar for long enough, you will see something like this. They're going to bubble, okay? They're going to give off some gases as it dissolves that calcium hard shell, okay? And you will end up with actually kind of a soft membrane. Now, this is not exactly the same as a cell membrane, but it's pretty similar in that it's going to be soft and it's going to be permeable to water. Now, if you put those eggs that have been dissolved of their shell into hypotonic water, let it go for a while, like 8 hours, and then compare what happens there to if you put it into corn syrup. Okay, so pure corn syrup, really thick, sugary solution, hypertonic, okay, and you let it sit. What you will find is that you'll end up with something very much like you see in this little video, and I just took a clip of it here, but it'll show you how bouncy and full of water the egg that was put in the hypotonic water solution will be, versus this other one over here. So let's just let this run. I think there's a little sound to this too.
From this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters a cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically salt water, water will leave the cell. Now that you're done with this experiment, time to play with those shellless eggs.
No!
Somebody wants the egg. Okay, here you can see.
You're just gonna...
And there is where they actually burst that egg that brought in all of that water, that egg that was in the hypotonic solution. So give it a try. It's kind of neat. And I will actually put the link to this video down in the description underneath the objectives that this clip will address. Okay? Give it a shot. There's nothing unsafe about it. The vinegar is an acid, but it's pretty much a household item. And you can actually give this thing a test. All right? Kids love it. So, and it's kind of neat. I mean, as an adult, I think it's kind of cool. So I will let it go, and we will move on to filtration and some active processes next time.